Through evolution, vertebrate brains have changed in both size and organization. The most primitive living vertebrate has a spinal cord, hindbrain, and midbrain, as well as a diencephalon and a telencephalon that contains cerebral hemispheres and subdivisions. This implies that all other vertebrates have these features. However, the cerebellum is very small compared to other vertebrates such as birds and mammals. This implies independent evolution, giving birds and mammals more complex processes. There is a theory that differences among brains are influenced by relative size. Mammals have a 6-layered cortex or neocortex. The cortex accounts for more than half of the brain's volume and is responsible for higher order functions. Reptiles were the first to show signs of large cortices. Brain size evolved independently in multiple lineages. There is a correlation between brain and body weight across multiple species. Linear regression can be used to show the mathematical relationship between the two. Using this information, we can draw conclusions about how many species deviate from expectations, known as residual regression. The deviation is equal to the vertical distance above or below the diagonal line on the graph. That distance is called the encephalization factor. The greater the encephalization factor, the more exaggerated the brain weight compared to expectations for mammal size. The encephalization factor is greatest in humans. Brain size is adaptation. Some capabilities, such as foraging for food and large song repertoires, among others, are linked to sizes of certain brain regions, while others are linked to overall cortical volume. There's a pattern that suggests that the human cortex has grown disproportionately over the course of evolution. The human brain continues to develop post-birth. For example, the medulla is fully developed at birth, but neurons are continuously added to the cortex as the child grows. This led to the theory that prolonging the later stages of development leads to larger brains. Many factors led to the rapid evolution of a large cortex in primates. Hominins are primates within the family of Hominidae, and Australopithecines are early bipedal tool-making hominins. The ability to use tools lowered the selection pressure to have larger jaws, so over time one can see the change in jaw size from these early hominids to Homo sapiens today. Australopithecus evolved to Homo erectus, which had a cranial capacity of about 700 cubic centimeters compared to the present day, where it is roughly 1,400 cubic centimeters. Brain volume reached the modern level about 150,000 years ago and now appears to be at a plateau, possibly due to the cost of having a larger brain. Negative and positive selection pressures affected hominin brain size. If the brain was any larger at birth, there would be a higher casualty rate among mothers and newborns. The brain takes up 2% of our body weight, but consumes very large amounts of energy from our metabolic budget. The social brain hypothesis states a larger cortex is necessary in order to maintain social relationships due to the high cognitive task it provides. Brain size predicts success in adapting to a novel environment. It is theorized that enlarged brains were an adaptation to help us cope with changing environmental conditions. It would be unethical to test this because there is no telling what an introduction of a foreign species may do to the environment in which it is placed.